Okay, I wanted to cover a number of things in this tutorial. First thing is this is September the 29th, 2023, and Raspberry announced a new Raspberry Pi 5, which is this little board here, and they've got a new chip, system on a chip, which is the ARM. Let me go down through here. First of all, this is just one of many announcements that occur on the web, but here's it features the 64-bit quad-core Cortex A76, which is what we have in the Orange Pi 5 Plus, but we've also got another Cortex core in there with 4 cores at 1.8 gigahertz. Anyway, they've got 2 versions of this thing, one with 4 gigabytes of RAM for $60 and one for 8 gigabytes, so it's cheaper, but it's only got, half the number of cores. And they're limited to 8 gigabytes, which is probably enough. But anyway, if you're interested. So first thing I want to show you is how to find out what you've got on your system. First thing you do is you do a sudo apt install lshw, which is a routine to list your hardware. Now I've got it installed, so it'll say, no, you've already got the latest version. Now you run it as root. So you do a sudo lshw, and it outputs a lot of stuff. The bigger the system, the more it outputs. Let me pipe this to more, because I only want to look at a couple of things to show you, and the rest of it you can study on your own time. So it shows that my system name up here is Colossus. Description, it's a computer, it's a product. It's got the RK3588 OP5 Plus. Width is 64 bits. It's 64-bit. And it's got a bunch of stuff here, but here we've got a CPU 0. And this is a CPU. And it can be clocked up to 1.8 gigahertz. It's got a whole bunch of other stuff. Here's the second CPU, CPU 1, also at 1.8. CPU 3 down here, okay, will also be clocked at 1.8. Then we get to CPU 4, and we get to the 2.4 gigahertz speed right here. And 5, 6, and 7 makes up to 8. So 4 of them are 2.4, and they are the high numbers, starting at, I have to do my math here, 4 through 7. On the right hand side here, I've got BTOP running, which shows me that over here I've got C0 through C7. Shows me that they're not doing much. And the clock here doesn't change. I'm going to do something else. Going back to the left-hand window, we got some stuff about internal buses and the bridges and everything, and then somewhere in here it has the memory stuff about the USB stuff. And if I've got, let's see, do I have anything here? No, that's all the time I want to spend on that. Sorry. Let me go to primes. I want to show you some stuff on benchmarking. You remember my primes program generate prime numbers, and I've got a shell script here that I'm going to compile primes. I'm going to move it to my bin directory so that when I come down here to execute it, I don't have to do a /. And prime says the program says it takes two arguments. One, the first argument is where to start. Next one is how to end, and I've got this thing set up for a reasonable time limit here, and it's going to output, because I'm not interested to look at it, output to 0001.out. And I'm doing all the primes from 1 to 50 million. All right, and I'm going to time it. Up here, I'm going to compile it every time. So to run this, I do a bash run.sh, and that will compile it, and then it'll start running. And if you watch on the right-hand screen here, you'll see that primes is running on CPU 4. Okay, now that's one of the 2.4 gigahertz systems, so it's running at, the fastest speed I can possibly get. Notice up here that this doesn't change, this 1.8 gigahertz on BTOP. And the job finished. So you see here it went from orange to back to the green, and there's the vertical number of dots here determines what percentage of the CPU it's using. The benchmark took 22 seconds. Now I did that so you could see where it was executing on the right hand. Now, if for some reason you want to run this on the slower process, there's a command called taskset, and you can specify which processor you want the job to run on. So, and it works. You give it a hex number 01, says to run on CPU's number 0. Let me get out of here. I want to type some stuff, but I don't want it to be a command, so I'm going to do a cat /dev/null, and now that says take whatever I type in now and just send it to /dev null, which means just throw it away. So this is the way it works. If you do a taskset 0x01, and then whatever what program you want to run, that'll send it or have it execute on CPU 0. Now think of the hex number 01 is in binary. How do I represent binary? I forgot what it was, but anyway, there's 8 bits in a byte, so this represents 0000001. That's equal to 0x01. If I go 0000010, that's 0x02. Then 0000100 is equal to 0x04. And those will each correspond to CPU 0. Then the hex 02 will be CPU 1. The 4 will be CPU 2, etc. So that's the way the numbering scheme works. So if I go back to my run.shell and I did a 01 here, this says run primes on CPU 0. So let's see if I know what I'm doing. Bash run.shell. Watch on the right hand side here, and we see that CPU 0 is now running primes. So you can force a job to go to a specific processor. If I want it, now, why did I kill it? I want to time it. So I know how long it takes to run on a 2.4 gigahertz to 22.763 seconds up here. This was running it on CPU 2.4. Now it's running on CPU 0. So the time should be the ratio of 2.4 to 1.8. And I don't have a calculator, but you know, it'll run a little bit slower. And this is if you want a task that you don't particularly care about and you've got other things that you want to give higher priority to, run on 2.4. That's the way you do it. So that's just something that may be of use to you. Let's see, this is going to take what? Let's guess at 1.4. I'm guessing 35 seconds or something. Somewhere 35, 40. I'm doing the math in my head. Did it stop and do something there? There was a glitch there. Wow. That doesn't seem right, does it? That's because something well, we'll look at that. Something for you to look at. All right, let me clear this. And here's what I wanted to do today. Oops. I wanted to show you something with some new or more detailed information about some programs called SED, TR for translate, awk, and we'll use mgdiff again. First of all, I have this program. This is the first program I ever wrote in my life. In 1966, written in Fortran. Now back in those days, we used IBM 36050, which was slow, maybe 45,000 instructions per second. And then I killed the machine even more because I'm doing double precision arithmetic, 64-bit floating point arithmetic. The IBM 36050 only had 4 floating point registers, each one 32 bits. In order to do double precision, it had to take the 64-bit number, put it across 2 registers, and then do the calculations, and it was slow. Anyway, we did program input on cards, and we used the IBM 029 key punch, and everything was in caps, no lowercase. Now, as a Unix, Linux user, I don't like caps. So how do you go about converting this to lowercase? Well, there's a command called translate, TR. In the early days of Unix, because of the way you set up peripherals and everything, they set up the I/O. There are 3 basic or default I/O units. Unit 0 is your input. Unit 1 is your standard out, usually to the terminal or to the screen. Input is from the keyboard, and then standard out 2 is your error or warnings, messages. So the translate command and the process of taking the output from one command to another, we have pipes, and it's called streaming, and a lot of the commands like sed and translate and the others are stream oriented. So what I need to do is, in order to translate, I need to first output RTO2.f. And if I do a cat, it just sends it to standard out. All right? And that's fast. So I'll cat RTO2.f. Then I pipe it to the translate. And I want to translate A through Z, the uppercase to lowercase. All right? And everything comes out, everything's translated to lowercase. I want to save that now. Cat RTO2.f, pipe it to translate A through Z to lowercase a through Z, and let me output that to new.f. So if I look at new.f, it's all lowercase. Okay? And VI now, did it do that for the lower uppercase? Let's see here. It's interesting. Yes. Vim does recognize things like keywords, like format. Down here, format is a keyword, do, undo, etc. So I know that my new.f is what I want, so let's just move it. Move new.f to rto2.f. Now when I do this, rto2.f goes away, my old caps version, which doesn't bother me. Now, because this was the first program I ever wrote, this was done in 1966, there were no computing science departments. There was a lot of stuff I had to learn on my own. First of all, I had to go through a physics book, Radiative Transfer by Chandra Shekhar, probably the only living person that's ever been through it now. Had to learn some numerical analysis. So this program solves partial differential equations. And I rewrote it in C because I've learned a lot about computing science since then and better ways to do things, and C is a better language than Fortran as far as I'm concerned. But I haven't compared this to my new C program, and I want to. Going back to the 36050, because I was paying $450 an hour for computing time, I couldn't use a whole lot of time, so I only got to do ninth order integration. Don't worry about that. It's just the reason this is a 9 is for two things. One, to save computer time, and then number two is my only output was to a line printer that had 132 columns across, so I had to restrict that. So another one. I want to up this number 9 to 15. How do you do that? Well, I could sit here with Vim and just, do a change word and change that to 15 and do that everywhere. But there's an easier way. And the way to do that is with sed, which is the string editor. Now, if you're going to modify a program that's running, recommend that you do it in a different directory. Save the old copy, but modify a new one. And let's do that. cp r2ot.f to backup. Backup. Now, if I cd to backup, there's r2.o2.f. Now, there's another file called sed.f. Now, sed, I could do this. I could do sed, and then I'll say substitute parentheses 9 with parentheses 15, and I do rto2.f, and this is going to output it to a standard out. So let's just look at what it does. This says run sed and give it something to do, substitute for parentheses 9 parentheses, left parentheses, right parentheses. I'll just not, you know what they are. Substitute this to this in this file, line by line, and then output it. So let's look at what it does. Well, goes down through here. Is there a left parentheses 9? Yes, there is one here. And it says, okay, let's do that one. But because I didn't give it any other additional information, it's only going to do it one time per line for the first occurrence. So the rest of these parentheses 9 parentheses don't get changed. So let's go back to my command. Let me clear this. And let's do this. Let's add a G here, and this says do it globally. For every occurrence on a line, do the same thing. So let's execute it again. Now we go back to this line and we see, okay, it did it. Wherever there was a left parentheses, 9, right parentheses, it put a 15. Now I didn't tell it to do 9, 9 because there's only one command I can do on that line. So in order to do multiple things to the same line, I have to have multiple commands, and the way that I do that is I make a file, sed.f, and in each line, I say take parentheses 9 and make it a 15. If I have a 9, 9, make it a 15, 15. So all the possible combinations that I have for indices on variables, it turns out I got 6 of them, so I want to change that everywhere. So now if I do this, I do a sed, and then instead of putting the quote, what I want to do, I do a -f, sed.f. This says run sed, and all the commands that I want to perform, they're in this file. I want to do this to r2.f. Let's output it to more. I don't know if I explained more. More says I expect a whole bunch of output, but I only want to see it one page at a time. So there's the first page. And if you'll look, you have to remember what I had, but in the first line there, it changed every occurrence of 9 to 15, does it here, and it doesn't mess up anything in the other lines that don't have parentheses, 9, parentheses, etc. The way more works here, if I hit a space bar, it gives me the next page. Space bar. If I hit return, it'll increment by one line. So it's a good way to control looking through a file. Let's see, I'm watching my time here. Okay. Well, I'm not watching it really good enough, but okay, well enough. Sorry about the English. Okay, I modified my program, right? What do you do with a program that you modified? Well, you better compare it with what you did before. Let me go back up here and to run rto2.f. I need to run a test case. I've got one here called 001, which has 2 lines of output. Says I want to do this for order 9 because that was the maximum I could. This has to do with one parameter on the atmosphere, and I want to go to this number on a parameter called optical depth. And that's the largest number I could do on an IBM 36050 without requiring $10,000 worth of real money. So let's run this. Way to run it is to compile it. So let's do, I need a make file, but let's G Fortran -F, no, automatic, minus standard equal legacy, -O rto2.f. Miracle. Execute it. Now I want to input 001 and let's send the output to 01.out. Let me time that. Time the last routine, and that took like 1/10 of a second, and that's not even optimized. Back on the 360-50 days, this took over 3 hours to do that. Hard to believe, but that's true. Want to do the same thing here, so we'll just run the compiler again. I need to copy 001 to here. Let's time that. So just not to confuse you, I'll go back here and run it. Time, 0.091. I want to compare the output of both runs. I'm going to use a program called mgdiff, which shows me graphically what the difference is between the two runs. So I'll take the 001.out from my new program and compare it with the output from the old program. And this is what the output looks like. On the left-hand side is the output from 001.out. On the right-hand side is the output from from the directory above 001.out. And if there's any difference between the two files, okay, we will get some stuff highlighted here. Let me show you an example. Let me vi rto2.f, and there's a parameter down here called h right here, which is the step size for integration. Once again, back in the old days, this was the value I used because I could not, I'd like to run it for a finer grid, but I couldn't do that because of money. So let's make this 1.0 divided by 2048.0 E0. Well, I'll make it D0 because it's Fortran, but okay. So this will, take more time and give me a finer resolution. So let's go back and time it again. Do you remember? Oh, yeah, we got our time there. Okay. Took 0.091 seconds to go 0.005. Let's see how long it takes to do it with the finer. What? Is there no difference between that? Let's compare again. I'm surprised that I'll have to do the math. 0.005, I guess 0.1 over 2048 is about the same number, but I expect the output to be different. It's not. Oh, you know why it's not? Because I didn't compile it. That's why you think I can't talk and think at the same time. All right, let's do the time again. There we go. It took 7 times longer. Also, I expect the results to be different. Let's see, how do I have to type? Now, there you go. You see the difference. You see that some lines are different than others. And let me make this full size. What is the difference between this line and the first line that's yellow and the second one? Okay. That number's the same. Oh, this one differed by 1 in the 6th decimal place. This one's the same. So they're pretty close, but there are just some numbers that are different. And you have to look. It does not show the difference on individual numbers. It just shows you by line. That's the lesson there. Did I get everything done? Now, if I look at the output, okay, shows me that I've got some text here. These numbers, the first column of numbers here has to do with the observation angle. If I'm on the surface and I'm looking up at the atmosphere, the angle of 0 is vertical and 90 is horizontal, and then these are intensities or irradiance values. and I want to plot those. I showed you how to do GNU plot. I need to feed GNU plot a data file, and I don't want all this other stuff in here to be included in the file. So look down here at the lower left side here, and you'll see a 7,5. That tells me that I'm in line 7. Okay, and then here I'm in line 15. Now I want those lines to be fed into GNU plot when I go to plot them. So I need to take those out and put them in a different file. The way I can do that is do a sed, and then I say 7,15 print, okay, 001.out. Okay. I got everything. Obviously, I didn't do it correctly. Did that on purpose. What I want to do is I want to not print anything except lines 7 through 15 of 001.out. So that just got me the data. I want to feed that to a file called 001 reflected.dat. So that'll just be what I call a data file. And then there's my data file. And if I want to plot it, then you remember that in my GNU plot, I had something that said plot point to the file that has the data, and then I had something like $1 or 1, 2, or I can do 1, 5 if I want the fourth. This is column 1, 2, 3, 4, 5. If I want to plot this column of data, then this is what I do, and I do lines and all the other stuff within the GNU plot command file. I'll come back and do this because I need to go off and make some runs, and then I'll plot the two, because I've never, compared the two except other than physically looking at the numbers. By the way, here where I'm demoing stuff without executing it, I did a cat and fed that to dev null. This is expecting all the input to be from the terminal, from the keyboard. This is a test and this is a test. And I can do this. There are two ways to terminate this. And the easiest way, or the correct way, is to do a Control D. The Control D is the ASCII character for end of file. So I'm going to hit Control D. That just terminates the cat command. Now, what have we learned today? Well, let's see. We learned to do a task set. We did translate. We did a simple example of sed. And I did mgdiff. Didn't get to awk. We'll get to it later. Now, for the sed command, or utility, or task, all the different names it can go by, there are enough books and there are enough YouTube videos to get into some really fancy stuff, but we're going to keep it simple. Okay, thank you for your time, and we will continue on. Hope you enjoyed this and learned something. And I did this in 35 minutes. Thank you.